Imagine a world where trains operate seamlessly, across borders at incredibly high speeds, and you never have to worry about a collision or like an unexpected stop. How do engineers actually achieve that kind of confidence in something so complex and so absolutely critical to our daily lives? Today, we're taking a deep dive into the European Train Control System, ETCS for short. Our mission really is to unpack the sophisticated modeling and analysis methods that underpin the rock-solid safety and dependability of these vital railway systems. We're going to explore the core insights engineers use.
It's been quite an evolution, hasn't it? I mean, you think back, railway signaling used to be very basic. Hand signals, simple block sections, only one train allowed at a time. Then maybe, around the 80s, we started seeing automatic train protection, ATP systems, things that could automatically break a train, stop it
Yeah.
overspeeding or passing a red signal. But the huge issue, particularly in Europe, was that every country kind of did its own thing. We ended up with, I think, at least 15 different ATP systems, totally incompatible.
Wow. Yeah, that sounds like a nightmare for cross-border trains.
Exactly, a real headache. So that's why the EU pushed for ETMS, the European Rail Traffic Management System. And ETCS is the core signaling and control part of that. It works alongside GSMR, which handles the radio communication. And ETCS isn't just about making trains run smoothly across borders, although that's important. It's fundamentally about boosting safety and reliability. Because let's face it, a failure in these systems, the consequences can be, well, severe, catastrophic even.
Okay, so let's unpack this a bit then. When we talk about ETCS, what are the actual core building blocks? What makes it tick?
Right. So at its heart, ETCS has two main halves. You've got the onboard system on the train itself and the trackside system, which is all the equipment along the railway lines. The onboard system basically drives the train based on data it gets from the trackside.
Okay, on board, what's involved there?
Well, the main thing is the European Vital Computer, the EVC. Think of that as the train's brain. It's constantly crunching data, making safety decisions, preventing overspeeding.
Yeah.
Then you have communication modules. The Balice Transmission Module, or BTM, reads data from those little yellow things on the track called balises.
Ah, yeah, I've seen those.
Exactly. And there's the Radio Transmission Module, RTM, for the continuous wireless link. Inside the cab, the driver sees everything on the driver-machine interface, the DMI, speed limits, targets, warnings, all that. And crucially, there's the juridical recording unit, the JRU. That's the train's black box. Absolutely vital if anything goes wrong. Oh, and the odometer, ODO, for tracking speed and distance precisely.
Got it. And trackside.
Trackside, you have those Eurobellises we mentioned. They're like fixed data points, storing information. Then line-side electronic units, LEUs, connect the bellises to the interlocking system that's the separate system controlling points and signals. And the central intelligence on the trackside is the Radio Block Center, or RBC. That's a big computer-based safety unit. It calculates safe movement authorities and beams them directly to the trains via radio. All these bits work together to guide the trains.
And you mentioned different levels.
That's right. ETCS isn't just one thing. It has application levels. Level 0, NTC for national systems, level 1, 2, and 3. They vary based on the equipment used and how information gets sent. Level 1 relies heavily on those balises for spot transmission. The train gets an update when it passes over one. Level 2, which is probably the most common one being rolled out now, is radio-based. The RBC sends continuous updates, and the driver sees the signals on their DMI screen. No need for line-side signals anymore.
Ah, interesting.
And level 3 is sort of the future goal. Fully radio-based, potentially allowing trains to run closer together, boosting capacity. The clever thing is, they're designed to be downward compatible, so a level 3 train can still understand level 1 or 2 infrastructure.
That's an incredibly complex web of parts all working together. But with that complexity, how on earth do you start to figure out what might go wrong? Or, more importantly, make sure it doesn't? And I guess, how do you even define what a failure means in a system like this?
That's a really key point. Precision is vital. So in ETCS, failures are typically grouped into 3 main types. You have an immobilizing failure. That's serious spammer. The system can't safely manage 2 or more trains. Basically, things grind to a halt. Then there are service failures. Performance drops. Maybe the system can only handle 1 train safely. It's degraded. And finally, minor failures. These might not stop the trains immediately, but they cause excessive unscheduled maintenance work down the line.
Okay, so how do engineers manage all that risk?
Well, the whole approach falls under the umbrella of RAMS. That stands for reliability, availability, maintainability, and safety. There are strict standards like EN 50126 or IEC 61508 that lay down the requirements. When engineers talk reliability, they use specific metrics, things like failure rate, how often a component fails, or mean time between failures, MTBF, the average time a system runs before it hiccups again.
Right.
And importantly, time isn't always clock time. It could be operating hours, number of cycles, or even distance, like kilometers traveled.
So, okay, we have the framework, the definitions. How do we actually analyze this? How do we model such a complex system to predict its reliability and, improve it? This is where it gets really interesting, isn't it? The tools they use.
Absolutely. This is where the clever quantitative work comes in. You essentially need two things: a way to represent the system, a modeling framework, and then an algorithm to actually do the analysis, to crunch the numbers.
Yeah.
Let's maybe talk through some of the main tools engineers use here.
Yeah, let's do that.
Okay, first up, you have fault tree analysis, or FTA. Imagine you have a really bad outcome. You want to prevent the top P event, they call it. Maybe the train having critical brake failure or something. FTA is it's a top-down method. You start with that bad outcome and logically work backwards. What single failures or combinations of failures could possibly lead to that top P event?
So it's like reverse engineering a disaster.
Kind of, yeah. It uses these logic gates. Or gates mean if any input happens, the output happens. And D gates mean all inputs have to happen. Its real power is identifying what are called minimal cut sets.
Minimal cut set.
Yeah, the smallest combinations of component failures that will cause that top-level system failure. It tells engineers exactly which failure combinations they absolutely must design against. It's like a roadmap for critical vulnerabilities, really good for big systems.
Okay, FTA. What else?
Then there's the reliability block diagram, RBD. Now, if FTA is about failure, RBD is more about success. It's a visual diagram showing how the system needs to function correctly.
So the opposite perspective.
Exactly. Think of it like a flow chart. If you can trace a working path through the diagram from start to finish, the system is operational. It uses structures like series, where everything in the chain has to work, and parallel, where maybe only one of several paths needs to work. Redundancy, basically. It's a classic approach been used for ages in railways.
Yeah.
It gives you a really intuitive picture of how success depends on the different parts. And interestingly, a parallel RBD structure, that's like an A and D gate in FTA. A series RBD is like an OR gate. They're related.
Right, two sides of the same coin in a way. What's next?
Next up is the Bayesian Belief Network, or BBN. This one's quite sophisticated. It's a graphical model, but it really focuses on causal relationships and probabilities. It shows how different factors influence each other.
Like a really smart decision tree.
Yeah, something like that. But it handles uncertainty really well using probabilities. Each element, or node, has a probability table saying how likely it is given the state of its parent nodes, its real strength. Well, two things: handling uncertainty and its diagnostic power. You can do backward analysis.
Backward analysis.
Yeah, if a system failure does happen, you can use the BBN to trace back and figure out which component failures were the most probable causes or contributors to that specific event. Super useful for finding weak spots.
I can see how that would be valuable. Okay, number 4.
Number 4 is the Markov method. This is what we call a state transition model. It's really good for analyzing systems that change over time, especially when you factor in things like maintenance and repairs.
State transition.
Yeah, imagine the system can be in different states, like fully working, one component failed, system under repair, system fully failed. The Markov model maps out how the system moves between these states and the probabilities of those transitions. The key idea of the Markov property is that the next state only depends on the current state, not the history of how it got there.
Ah, okay. Memoryless.
Precisely. This makes it great for modeling the impact of repairs. How quickly can we get from a failed state back to a working state? How does that affect overall availability? It's widely used for RAM's analysis and signaling.
Makes sense for systems that get fixed. And the last one.
Lastly, we have Petri nets and their various extensions. This is another graphical state transition model, but often seen as a bit more flexible than Markov models, especially for complex interactions. Think of it like a system with tokens representing maybe resources or system components moving between places, representing states.
Mutants in places?
Yeah, and transitions, which are like events, maybe a failure or a repair finishing. When a transition fires, it moves tokens around, changing the system state. It can be really powerful when the system states aren't immediately obvious or when you have lots of things happening concurrently.
How does it relate to Markov?
Well, if you define the transition firing times in a certain way, like they happen instantly or follow an exponential distribution, a Petri net can actually become mathematically equivalent to a Markov model. But they offer more modeling freedom. Often, for really big systems, engineers might use extensions, like maybe driving a Petri net model from an RBD structure, and then use things like Monte Carlo simulation to analyze it. That gives another way to check the results.
Wow, okay. That's quite a toolkit. So let's bring this back to Earth. Take ETCS Level 2, that common radio-based system. How would engineers actually apply these methods to it?
Right, good question. Let's look at the ETCS Level 2 onboard subsystem, so the gear on the train. You do a structural analysis, maybe using FTA or RBD. You map out how the EVC, the RTM, the DMI, all those bits are connected, and you immediately see the importance of redundancy.
You mentioned that earlier, the backups.
Exactly. The EVC, for instance, often uses hot standby, two vital computers running in parallel. If the main one has a glitch, the backup takes over instantly, seamlessly. Other parts, maybe like the DMI screen, might use cold standby. The backup only powers up and takes over if the primary one actually fails.
Okay, so how does FTA help quantitatively?
Well, you can build a detailed fault tree for the entire onboard system failing. And using the known failure rates of individual components, the DMI, the BTM antenna, the TIU, the EVC itself, you can calculate the probability of that top-level failure. For example, you could calculate the probability of the whole onboard system failing within, say, 10,000 operating hours.
And that tells you where the weaknesses are.
Precisely. You might find that even if individual parts are reliable, certain combinations, maybe involving communication links, contribute disproportionately to the overall risk. That highlights where design improvements might be needed.
And what about repairs? How does that fit in?
That's crucial. The initial calculations might assume parts fail and stay failed, but you can refine this by assuming components are repairable. You factor in things like mean time to restoration service. Maybe a train can operate with a minor fault for, say, 4 hours until it gets to a maintenance depot, or the actual mean repair time. Maybe it takes 8 hours to swap out a faulty module.
And adding that changes the picture.
Dramatically. It significantly impacts the overall system unavailability, how often the system isn't working when needed. Good redundancy plus efficient repairs make a system much more resilient.
Okay, and you mentioned the Bayesian networks for looking backwards.
Yes, this is really powerful. You can build a BBN based on the fault-free structure. It can also calculate the overall hazard probability. But the key is that backward analysis. If a hazard does occur in operation, you can plug that observation into the BBN. It will then tell you which specific components or subsystems, perhaps the DMI failed or there was a BTM communication issue. They're particularly good for analyzing complex, redundant modules with repair, like the EVC itself. Remember, the EVC is often a double 2 out of 2 system, very redundant. 2 channels, each internally redundant, acting as hot standbys for each other.
Right, layers of backup.
So a Markov model is perfect for this. You define states. Oh, okay. One CPU failed in channel A failed, channel B active, both channels failed. System in repair. The model shows the transitions between these states, including the repair transitions. This lets you calculate things like the probability of reaching a hazardous state, or the overall unavailability of the EVC module, considering its dynamic behavior and repair process.
And Petri nets could do something similar.
Yes, you could model the EVC using a Petri net too. Tokens could represent the state of CPUs or channels moving between working and failed places via failure or repair transitions. Again, great for complex interactions. And often, engineers will run Monte Carlo simulations on these PetriNet models. Thousands, millions of simulated runs.
Why do that?
It provides a way to verify the results they got from the analytical Markov calculations. If the simulation results match the math, it gives much higher confidence in the reliability assessment. It's like a double check.
Okay, that makes sense. So this depth of analysis applies to the trackside stuff too.
Absolutely. Similar fault tree analysis is done for the trackside subsystem, the RBC, LEUs, balises. There might be differences, like maybe using triple modular redundancy for really critical trackside parts. And the really powerful thing is you can start connecting these models. Imagine multiple BBNs, one for each train's onboard system, one for the RBC, others for trackside sections. By linking them, engineers can actually model the reliability of an entire operating line with multiple ETCS-equipped trains interacting. That gives you a truly system-wide, holistic view of safety and reliability.
That's incredible, taking it from single components right up to the whole network.
Exactly. So just to kind of wrap up the methods, fault trees and RBDs are your go-to tools for understanding the basic structure, the static logic of failure and success, especially in large systems. Bayesian belief networks bring in probability, handle uncertainty really well, and they're fantastic for that diagnostic, backward-looking analysis. Why does this happen? And then Markov models, And Petri nets are essential when the system dynamics matter, when components fail, get repaired, and the system changes state over time. Especially good for complex concurrent stuff.
You can really see why understanding these methods isn't just, an academic exercise. For anyone listening who's involved in real ways, whether you're studying engineering, just starting your career, or you're a seasoned pro working on safety, these tools are absolutely fundamental. They're what allow engineers to build these incredibly complex systems with real confidence, to actually predict potential problems before they occur, and crucially, to keep making train travel safer.
And it does raise a fascinating question for the future, doesn't it? As these railway systems get even more connected, more digital, maybe even moving toward higher levels of automation, how do these reliability modeling techniques need to evolve? How do we ensure that pushing the boundaries of technology never, ever compromises that absolute bedrock requirement of safety?
Yeah, that's a constant tension, isn't it? Balancing all that amazing complexity with the ultimate goal, flawless, safe operation every single time. Definitely something to mull over until our next deep dive.